the main theme here is we're going to talk about moving our Kafka deployments from EC2 onto Kubernetes and all the fun challenges that went along with that. So there's 5 main parts of this that we're going to talk through. So we'll go over just a little bit of the background of Kafka at Robinhood and like the motivation. The second thing, we'll talk through the design, some of the decisions we made on our like how we solved this problem. Third one, Moon's going to talk about the actual migration process, which is pretty interesting, and some different ways that we did migration for like a huge stateful service. Then I'll talk a little bit about some challenges we face, and then we'll wrap up with a few lessons learned. Okay, so starting off, so just like a little primer on Kafka at Robinhood. We have pretty large-scale deployments. We've got about 50 clusters now. We've got hundreds of brokers across many different use cases. So it's used very widely just for asynchronous communication between microservices. And we also have some pretty critical use cases, such as things like pricing information for equities. That's very latency sensitive, and things like order flows. And then the last piece here is really talking about how we deployed Kafka in the past. So we used the Confluent platform binary, and we would just install that onto EC2 instances using something called Saltstack. And then those brokers were just running on EC2 instances, kind of just in the data plane without much notion of control plane. So on that subject, this chart's just showing a little bit of the company-wide trend towards moving services onto Kubernetes. And so kind of fast forwarding to the past year or so, really Kafka was one, if not the last, infra that was still hosted on, or basically deployed via Saltstack. And so that was one of the big motivations here, is to kind of like move everything over to Kubernetes, and that includes Kafka. And so that's why we decided to try and solve this problem. But in doing that, we also were able to gain a lot of other benefits here. Essentially, creating new Kafka clusters with Saltstack was very difficult because everything was kind of disjoint. Again, there's no real notion of declarative infra or control plane here. Whereas now with Kafka on K8s, we have a custom resource. So you have like a single config. Everything sort of, all the dependencies are deployed with the cluster. And it takes about a day, but a lot of that is just sort of like propagating that through Argo CD and things like that. Another piece here is that, as I mentioned before, we treated these brokers as sort of like inert servers that we don't want to touch much. So when we do have to make changes, a lot of them are manual, or we would SSH into one of these boxes. It makes things slow, and you kind of have to go box by box. Whereas now we have this notion of declarative infra, and we can basically make config changes and do GitOps on that. Another piece is that as I was mentioning before, as a company, we're supporting 2 different deployment pipelines, and we really wanted to move everything over to Kubernetes, and I think that makes much easier to maintain one paved path. And then lastly, this also enables faster velocity to do things like version upgrades, which can also catch up to you if you don't upgrade your Kafka version. Okay, so moving on to the design and like some of the challenges that we wanted to. So what I wanted to start by showing you guys is just to kind of let this sink in and just get your minds wrapped around this idea that we essentially want to deploy Kafka across multiple Kubernetes clusters. And the reason for doing so is that we want to prevent a single point of failure, and we consider like a Kubernetes cluster or the control plane within that, the API server, etcd, all those things. If that fails, we don't want all of that to affect our entire Kafka cluster. And so we replicate over multiple Kubernetes clusters. And that's one of the cruxes of the challenges here, is we want to design a control plane that really works across Kubernetes clusters. And so what you can see here in the picture, each of these horizontal boxes is a Kubernetes cluster that has a different color. And you have the control plane on the left. So there's a controller that sits in each of those Kubernetes cluster. And then there's also the data plane, which we would have each Kafka cluster in its own namespace. And each of those has a rack, which you may be familiar. A rack is sort of an idea of like a failure domain, where if we have essentially 3 copies of the data, each of them lives in one of these racks, so that if one rack goes down, you still have 2. So that's kind of the end state, and I'm going to show you kind of how we got to that. So and another little kind of introduction on Kubernetes. There's a few different ways that you can automate things within Kubernetes. I'm sure a lot of you have used Helm charts in the past. It's like a very simple, lightweight way to do templating to template manifest for different environments and things like that. You can also write custom code to do templating. We have like a Golang service that essentially does that at Robinhood. That's sort of the middle option. And then on the right-hand side, we see like Kubernetes operator. It's sort of the most complex, but it gives you the highest level of automation, and you can sort of define whatever custom resources you want. And so on the left here, I kind of boiled down exactly what requirements we needed, or sort of like the level of automation that we really needed. And I think one of the biggest things was the rolling upgrade. We really wanted to automate that process with Kubernetes. Like I said, if you want to do like a version upgrade, the Kubernetes machinery should know enough that it knows how to cycle brokers in a way that's smart and avoids downtime and things like that. And the other key thing here is like we really wanted to be able to get at individual brokers. There's times where we want to quarantine like a specific broker that's having issues, or we want to scale up a volume on a specific broker. And so that's another key consideration here. So kind of taking some of those constraints, we sort of map those out, which you can kind of see the Venn diagram. Some of those things we talked about, we want it to have this sharded control plane. We want to sort of like have the right level of automation, but also limit the risk that we're really introducing from this sort of inert, like these servers that we don't touch, into something that is in a more dynamic environment that's running on pods that could be churned and things like that. And then the last piece is just really like making sure that the choices we make work with our ecosystem and tech stack. There's a lot of operators or things out there off the shelf that have opinionated choices on other technologies they want to use that we don't necessarily want to take on. And so kind of like when we sort of look at that picture, what made the most sense for us was actually choosing to write a custom operator where we really want to be specific exactly what that operator is doing and limit the amount of risk that we're introducing to the system, because we have critical use cases running on these clusters. So I'll show like a super high level. So as I mentioned before, the custom resource that we define is the Kafka rack. And each cluster is going to be made up of 3 Kafka racks. And these racks are essentially deployed in separate Kubernetes clusters in production. I only really show one field in the API here that I think is important, which is that we have this array of brokers, which a broker is essentially like an ID and the configuration for that broker. And so the purpose here is like, it's hard. So the typical stateful abstraction in Kubernetes is called a stateful set, and they don't really let you look at these as individual brokers. They just treat it as a set of brokers. And so what we wanted to do is really, with this array, you can sort of like get at individual brokers. You could change the configs for individual brokers. You can have heterogeneous like volume sizes and all of that. So that's what that's showing. I'll show just like a few other features here, and kind of the way we break down something like a broker. It's represented as a pod that has a config map that's has like a broker config, metrics config, things like that. It is bound to a PVC, which is how, where is connected to a volume that's backed by EBS, and then there's also a service for each of those pods. And essentially, there's different, like if you guys know much about the Kafka broker configs, they sort of split them into different categories. So some of them are per broker. They're basically dynamic configs that could be changed per broker, and they don't need a restart. And other ones, they do need a restart. They're read-only configs. And so for the read-only configs, what we do is we basically trigger a rolling update that will churn one pod at a time. And during that churn, we're basically health checking with an admin client to see that there's no URPs. And then once we see the cluster is healthy, we can proceed to the next one. So that's how a rolling upgrade works. And then the second case is that there's dynamic configs. And so that's what this diagram is showing here, where we embed the admin client into the controller. And that can basically, describe config and alter config and basically, within the reconcile loop, alter the broker config without any interruption to the pod itself. And yeah, we did a lot of work around essentially like making sure this is very fail-safe, that essentially that the data plane, like the controller kind of fails static. So like if the controller goes down, we know that these pods are operating, and there's essentially nothing happening that's going to lead to unavailability of those pods. Okay, so the other piece, so there's other details here, but I think some of the other interesting pieces here is how we think about deployments, because again, this is something that we're kind of automating now, and you guys know like there's a lot that can go wrong, and so there's really two classes of deployments that we care about. So one is we're deploying changes to the Kafka cluster itself, and the other is around deploying changes to the Kafka operator itself. So I'll talk about the cluster version first. So we have these different clusters. Their different use cases are essentially hosted on these different clusters. And so you see here that we kind of set this up like a pipeline where we deploy a set of resources. And within each of these deployments, we're going to deploy like the latest commit, and then we run a bunch of tests, metrics tests, and also like an integration test or end-to-end test. And then we also give like a bake time. And as we're running those tests, if at any point it fails, we stop the deployment, and that limits the blast radius so that like at most we have one rack down, but we wouldn't lose availability there. We also have situations where we're essentially sharding the Kafka cluster itself, but you could imagine that this extends to that, where you could sort of like sequence these. If you can imagine like, this box on the left, if you just basically, had more of those in series, that would what the sharded version looks like. But yeah, the main idea here is just really limiting blast radius for bad changes. And we do something very similar for the operator. So this is showing essentially like the orchestration for these deployments is through something called AWS Code Pipeline. And so this is the deployment's kind of moving top down here, and as it goes through these steps, if everything's looking good, it's going to give like a green check mark, move to the next step. If something fails, then it's going to block the deployment. And so we kind of do the same thing here, where the controller is sharded, and each of those controllers essentially manages one rack. So again, if there's a bad, let's say someone makes a bad code change and they try and upgrade the controller, that would just affect the rack, one rack that controller is associated with. Okay. So now Moon's going to talk a little bit about the migration.
Cool. So basically that design allowed us to get all the things in place to actually run Kafka on Kubernetes. But the other part of the work is, how do we actually migrate our, actually existing brokers onto Kubernetes? Because these brokers are serving live traffic, and downtime is not very fun for anybody involved. So this is kind of like a high-level overview that kind of walks us through the migration process here. So On the way on the left-hand side here, we have the code generation where basically we do a lot of things to make sure there's a lot of automation here. Obviously, in migrations, a fat finger is the worst thing that can happen to anybody overseeing that migration, and so we try to minimize that as much as possible. And in the middle here, we kind of bifurcate between two different migration methods. So if it's not a super large cluster, then we prefer to do this, what's called a rebalancer migration. And this is kind of like the idea of like a stretch cluster. So you already have your existing set of like EC2 brokers. You basically append a specific Kubernetes broker. And then you basically migrate the set of topic partitions to that specific Kubernetes broker from a specific corresponding EC2 broker. And then on the bottom hand here, obviously for Robinhood, we have a lot of data on some of these Kubernetes, on these Kafka clusters. And we have to be ready in terms of market open. So we have a pretty tight timeline with respect to how long a specific repartitioning can take. And so when we ran into that, we decided to basically do this other type of migration, which is an EBS volume migration. And the crux of that is reusing the specific EBS volume that was already attached to the EC2 broker at hand, and then reattaching it to the Kubernetes pod. And when that's all said and done, we can rejoice and update the CNAME record, and then basically point that to the Kubernetes service at hand, and then basically clean up the EC2 brokers. So that's just kind of like a high-level overview of the migration process here at hand for us. So I'm going to delve a little bit into the code generation part. Basically, the crux of this specific step is that we actually run this migration script that automates a lot of this for us. And the automation happens from our existing EC2 brokers at hand. So like we run this script, the script actually just SSHs into the specific EC2 brokers at hand, fetches the Kafka server.properties file because that's where we override specific properties across different Kafka clusters. And we basically use that as the input to basically generate all the specific Kafka rack CRD that Nathan just talked about in the previous slides. And there's a little bit of fluff in the middle too. That's probably a bit more specific to Robinhood. But we deal with a specific object that's a little bit on a higher level than the Kafka rack CRD at a certain point here. And so from there onwards, we generate the specific kube manifests that end up becoming the Kafka racks that get applied by Argo CD and code pipelines, as Nathan explained in the previous design slides here. And also, there's concept of why generate, fat fingers are also always the worst things that can happen to a migration operator at hand. But also, in a way, a lot of these configurations are, shared among different Kafka racks. For instance, num fetch replicas or something, network IO threads. A lot of those things are same across all three different Kafka racks that you have. So, in day-to-day, it's actually kind of nice having a higher level object where you don't necessarily need to, repeat a lot of these across different Kafka racks. And if you do need to, tweak something underneath the hood for a bit more minute granular detail, you can always refer to the underlying Kafka rack object as necessary. And also something a bit more, specific to Robinhood is that specific CRD that I'm talking about that, resides on top of Kafka rack. That also gives us the ability to inject a lot of the things that our Robinhood stack gives us for free. One of which is the specific sidecar that we actually need to generate the certs to run PKI effectively. And so this the CRD that I'm talking about is kind of dubbed the archetype. But basically, the framework gives us some of these code generations and dependencies for free. And we can piggyback off of these via the code generation steps that we explained before. So we don't necessarily need to reinvent a lot of these different sidecars and so on and so forth, and how to inject them with the specific correct CPU and memory requests and so on and so forth that our central team manages. So this is kind of like the first procedure that I was talking about when I was talking about the initial high-level migration methods here. And so this is the idea of the rebalancer / stretch cluster method. And so you have your original set of EC2 Kafka brokers on the left. You launch a new Kubernetes Kafka broker, and you simply run the rebalancer to reassign the partitions from the EC2 broker that's running in the same AZ to the same Kafka broker that's running in the same AZ as well. And so like basically you do a Kafka reassign partitions underneath the hood. There's no inter-AZ networking fees here either because you're moving data between the same AZ. And once that's all said and done, you just terminate the obsolete EC2 instance. Now this is great, especially it worked very well in our pre-prod environments because some of these pre-prod environments have very little data. So the reassigning of the partitions actually takes a very short amount of time. But when it comes to prod, especially because our previous paradigm of EC2 Kafka clusters meant that it was hard to create more minute clusters. So we had these kitchen sink clusters with a lot of data. And basically for those, if you were to reassign the partitions, there was no guarantee that it would be complete by market open the next day or even over the weekend as well. And so we basically need to create a different migration method here. And so basically here is the EBS volume method that we ended up doing. So on the left-hand side, Sam again, your original set of EC2 Kafka brokers. We created this migration script that runs the EBS migrations for us. Basically what that thing does is that it creates it basically conservatively creates an EBS snapshot just in case something goes awry. We haven't had to use it yet, but it's something that we do. And then basically what it does is that it creates the underlying PV from that EBS volume and applies it to the specific Kubernetes cluster at hand. And so what happens then is that when you have this and then you apply the Kafka rack, with the PVC that pertains to the PV, that pod will basically be pending because it can't necessarily attach itself to that EBS volume because we have multi-attach volume disabled. And then what you end up doing is that you terminate that specific EC2 instance, and now the Kube pod can magically come up with that specific PVC and the underlying EBS volume attached to that specific node/pod at hand. And so this is great for us because for those really large clusters with a lot of data, it's basically the only real bottleneck is basically the time to delete that specific EC2 instance. So there's a pros and cons here between procedure 1 and procedure 2. We prefer procedure 1 because it's simpler. There's no downtime of brokers at all either. There's no URPs being caused by this because of the fact that you're piggybacking off of the very robust Kafka replication / reassignment of partitions. Now the biggest con was duration, like I reiterated before. There's no guarantee that our reassignment will be over by the time that we actually needed all the throttling to be lifted, all the replication throttling to be lifted by market open, especially because market open, we do get a lot of spiky traffic. So basically for procedure 2 though, we have the pro of having it be a lot quicker. But the con is that there is a downtime of a single broker in a rack at a time. And rollback scenario could be a little bit more complicated depending on the state of the EBS volume at hand. But that's why we end up doing the EBS snapshotting so that could be used when we actually need to. So we ended up doing a lot of procedure 1 in our pre-prod environments, and procedure 2 is our preferred method for our prod environments with a lot of data. So I'm going to hand it over to Nathan to talk more about the challenges that we faced during this project.
Cool. Cool. So one of the things that we spent a lot of time thinking about was reliability and performance. And I think essentially hosting Kafka on Kubernetes presents some new challenges. And here's sort of one piece here where we want to again eliminate the SPOF or the single point of failure. And so in the EC2 and Saltstack world, it's pretty simple to understand because the EC2 instances are hosted in different availability zones in AWS. And so you kind of treat that as separate data centers in a certain way. And so we basically have, one of those each of those racks in a separate AZ. And then when you think about Kafka on Kubernetes, now we're sort of in this two-dimensional space where we need to map the failure domains. On one axis, we still have the availability zones, but now on the other axis, we have these different Kafka clusters. And so what we ended up doing was kind of trying to stack those to minimize the complexity, so that we don't have this Cartesian product of those two axes. And so that's kind of showing the second image here, where we sort of like bound each of these racks to an AZ and a Kafka cluster, and it sort of simplifies that a little bit. There's an additional thing that we need to think about here, which is if say we do have a control plane outage or we do have an AZ outage, how do we sort of like migrate resources between Kubernetes clusters, especially things like volumes. And so we basically developed scripts to do that. And so these racks are actually portable across the different Kubernetes clusters. And I think the other thing that another challenge that we ran into was that, again, we were running the Confluent platform binary, and now we're running the container image, which, like, in theory should be pretty straightforward, but there are certain things, essentially the way that we assign resources and sidecars and other things. Okay. Another piece that we thought a lot about was that we wanted to do like sort of zero downtime migration, or at least minimal downtime. And so one of the main things that we exploited was the concept of the stretch cluster. So the diagram here is showing, like, it's sort of a modified diagram of a stretch cluster that I found, kind of showing what we're doing here. So on the left-hand side, you see the EC2 salt cluster. That could have could have a couple of brokers, or it could have 20 brokers or whatever it is. And then we have this secondary cluster that's a Kubernetes cluster. We bring that up in parallel, and we essentially migrate those over. And what you end up having is the Kafka cluster is cohesive, but it's being hosted in different data planes essentially here. And so I just showed 2 brokers here, but that number could be 9, or it could be something else. Another thing that helped a lot was that Moon kind of talked about the CNAME. So we essentially pointed our clients at like a static CNAME that maps to essentially maps to the EC2 address originally, and so. That was helpful because we didn't have to change any of the client code. The clients are still pointing to that same record, and it can bootstrap the servers from there, and then it can talk to any of the clusters or any of the brokers that's in either one of these clusters. And again, as we said, eventually we can sort of cut over to behind the scenes. We can cut over to the Kubernetes service. And then the other thing, we had a pretty robust rollback procedure. So if anything went wrong, we were able to sort of and because we're moving one broker at a time, that helps a lot too. And then we also had like a pretty extensive checklist as we're migrating these. And yeah, I'm proud to say we really didn't have any adverse effects during the migration. Everything went pretty smoothly. And I think that was like a testament to just really thinking through all those problems. Okay, and then the last piece is really like the deployment piece, where again, like if you're thinking about where are you going to have like some issue that's affecting availability or data loss or some issue, it's a lot of times it happens during deployments. And so we did a bunch of things to sort of to make that safe. So one thing was doing validation. So there's like a lot of configuration here. Starting from what Moon talked about, there's essentially like a API at a cluster level, and that generates multiple resources below it, and there's like a pretty extensive API as far as the things that we need to expose to be able to configure these correctly. And so we put tests in different places. One is in the Bazel build graph, which is where we're generating all this code, and then the other place is in the validating webhook that's running in the controller pod. The idea of the validating webhook is that you may want to, express some logic to validate more complex changes, and you want to do that at runtime, and so that happens in the validating webhook. The other thing we want to do, again, like limit blast radius of bad changes, and so you saw the way that the code pipeline works. It's sort of deploying things step by step. And we also have, in the controller, we have that health check. And so that So the health check is essentially going to limit the blast radius pod by pod. And then code pipeline's kind of the thing that's coordinating these deploys so that we know we're only doing rack by rack. And so with those two things, you really have this deployment's very encapsulated so that any bad change is going to affect a very small part of your deployment. And then the last piece is on monitoring. So we also added some custom metrics and things in the reconcile loop. And again, that kind of gave us more confidence that, and just a quicker time to see like if a custom resource is sort of stuck in a rolling update or something, we would know that pretty quickly. Okay, and I'll hand it back to Moon for lessons learned.
Yeah, a few lessons learned during this process. First thing is automation is golden. So limiting human workflows or interactions it's pretty nice. Like, previously when we had to do a lot of these, OPSI stuff on our Kafka brokers, like our fat fingers always took over here and there. And so there were a lot of manual errors that happened that would bite us in the end. But in not only the migration process here, where we do end up automating a lot of things, but overall just moving to Kubernetes and making things declarative means that everything can be powered by GitOps as well as safe deploys, where if you do want to make a change, it goes to the proper peer reviews, as well as the fact that now you have an operator that babysits your changes for you, looking at URPs and so on and so forth, so that you don't end up causing reliability issues at the end. So what that all results in is that you end up doing less on-call toil and babysitting. Simply just describe what you want, what you want to be reality, and the operator / the system just takes care of the rest for you, and that's pretty nice for us as people who babysit these as on-call engineers, so that you don't necessarily need to be waking up at 3 a.m. or something because something you ran at 11 p.m. just caused some outage or URPs. And so, the smarter deployment pipeline that's cognizant of application health, for instance, for our use cases, URPs and offline partitions is something that's pretty useful. And so what this all culminates in is that, if you have easier management of the Kafka clusters at hand, you have more frequent upgrades and changes. But also, you have more, you have less friction towards, cluster creation as well. So, previously in our, version of EC2 world, you would have these kitchen sink clusters because of the fact that we wanted to have a large cluster that satisfied a lot of needs. But hopefully, going into the future, we can create more specialized clusters with configurations of replications or whatnot set to specific, latency needs of the specific applications at hand. So, this kind of allows us to set up the future for, breaking up our kitchen sink clusters to a bit more of a specialized cluster that serves each specific individual needs a little better. Also, we ended up, fleshing out a lot of risks earlier on. We conducted dev readiness reviews to, launching this in our pre-prod environments, but also, prod readiness reviews so that, when we do launch this in prod, we don't end up, causing a lot of, unforeseen reliability issues. And so we, roped in not only our team, but our container orchestration team, which is our team that manages our Kubernetes clusters across the board, as well as our other teams that manage the underlying nodes themselves. And so we try to break the system early in design and did a lot of chaos / load testing to make sure that whatever we're doing here doesn't actually cause a regression in any sort of reliability that we had in the EC2 world as well. And so, yeah, interesting things can happen at the limits. So we try to emulate those limits as much as possible.
Okay. And yeah, one of the big takeaways here was just there's an Einstein quote that says everything should be made as simple as possible, but not simpler. I think that was something that came to mind as we think about the approach that we took here. I think some of the art in engineering is sort of figuring out where on the continuum of over-engineering to under-engineering you want to be in that perfect middle spot where you're solving the problem adequately, you're not adding risk, and you're really thinking through things in a way that you can make something very simple. Like for us, we expose a very simple API, but we can do a lot of powerful stuff with that. And yeah, we just wanted to shout out a bunch of people that were instrumental for helping us on this project. There's more than the list here. But yeah, thanks to everyone that helped. Our colleague V is also here. She's been a big part of the team.